Okay, welcome everyone to Lovelace 10 at noon. Coming up, we have karnei Gozman, who is a systems designer from Detroit. He's giving a talk on introduction to quantum perturbation. And let's give a big round of applause. Thank you.
Hello. Sorry. Ah. So, quantum perturbation is sounds like a really complex aspect of quantum mechanics, but it's actually, in simple terms, it's the shaking of a wave. In quantum mechanics, there's a lot of emphasis set to waves and what are waves, and that's what my talk is about. And how can we use it? What can we do about it? And just random facts from the internet. My disclaimer for this talk is that I'm not a mathematician or just pretty much nobody that got interested in this topic and started researching. But notice how there's a tilde next to the facts, so you should really verify your own information. Indicates sort of facts, wiki facts. Uh, I'd like to speak for half the time, or roughly a little more than half the time, and hold your questions till the end. Mostly, probably because I don't know the answers to your questions. I can tell you right away. It's just going to be like that. But if there's something I need to clarify, I probably won't anyways. So we'll just wait till the end. So, um, and then that's my disclaimer. So, wait, what? Why are we dealing with waves? Waves are actually a common component of everyday life. A lot of things in macro world are waves also. Uh, it's interesting for us to look at waves because they can be foretelling of what's going to happen next. Especially in harmonic systems, a wave is considered predictable because you know where it's going to end up. It's following a predictable trajectory and it goes up and down. Um, a full definition of a wave is actually very hard to encompass. Um, and so I will begin with another set of disclaimers. Basically, the quantum mechanics is still not understood completely, and you should pretty much ignore anything that anybody says after, according to quantum mechanics. And so, let's take a look at waves. Waves, like I said, on the macro world, on our human-sized world, human scale, we see pendulums as an example of a wave. But on the micro world, inside of atoms, around atoms, on the nuclear scale and the subatomic scale, there are waves that we can use to make predictions whether reactions happen or not. So for our purposes, we're just going to look at waves and not necessarily one-dimensional. A single all-encompassing definition for a term wave is not really straightforward. You can have disturbance traveling through a medium by which energy is transferred from one particle of the medium to another without causing any permanent displacement of the medium itself be considered a wave also. But also a particle has coordinates, and those coordinates can be tracked as a wave as it bounces from place to place, as I'll talk later about. For example, optical activity is also happens in waves. Photons travel in a certain trajectory, and they bounce around as a wave. And we can see that in optical activity because if we change polarization of a medium that it passes through, it can't pass anymore because it's being cut off. Um, Oceans have waves, tides, and word origin. Um, who knows? Where did the word wave come from? Maybe it's just some guy waving his hand. So, as I said, particle systems can be explained in waves also. For example, when you shake, where's my mouse? When you shake a connected graph, you're actually perturbing the coordinates of all the other nodes associated with that item. So as you're perturbing one node that's connected to all the other nodes, you're altering its position, and that's a perturbation of its position, if you consider its coordinates as a wave. One interesting aspect of the perturbation theory is that it was based on Hamiltonian theory, which was a system of dynamical governed equations in physics that help you deduce motion of planets and pendulums, any kind of harmonic systems that when you apply other modifiers to it, you can still predict what the outcome is with more and more accurate precision, the more you calculate it. Sorry. This is another perturbation. This is closer to, it's essentially the same thing. You're shifting positions of particles. And so this is kind of leading on to what a dynamic billboard table is, which is, sorry, my notes, I do. Right. If I could just wing it. The interesting aspect of a dynamic billiards table is it's a system where particles alternate from straight motion and specular reflection. It's like a billiards table, except that the boundaries are not restricted to simple rectangles. So the math involved in the specular reflection off the edges gets a little more complex. But in essence, that is a wave that's being perturbed by the borders. Just another way of thinking about what the waves are. Harmonic systems have a predictable, as I said earlier, they have a predictable path of information, the trajectory. They oscillate in a certain predictable way. And as you perturb this system, you get a slightly different graph. But if the disturbance is minute, you can still make predictions and calculations of where the path will go to. Should have been the first slide. Diagrammic representation of Rayleigh-Schrodinger perturbation theorem. So there's a concept of eigenvalues, and eigenvalues are, there's a very complex definition of how you can use eigenvalues in transformation using a matrix. But to me, I'm not a mathematician, so I just like to think of it as integers. It's a form of floored values that have a specific quantized value. They can't be in the middle. That's how I perceive it to be. If you have an eigenvector, that vector can be modified. That's what it's set up for, across the whole list of items. So in many instances, it can be thought of as a list of real numbers called elements, an eigenvector. Eigenvectors of a square matrix is a non-zero vector that, when multiplied by a lambda, that's supposed to be, yields the original vector multiplied by a single number. So here we can see that basically you're amplifying a set where it was xy was at one point, lambda y, lambda x is at a different point. And it's really this. This is an example of perturbing an eigenvalues for a graph, for an image. You're altering, you're just transforming it. It's also a perturbation of it. And and I guess Mona Lisa wants to stay up there for a while. It's just going to be like that. All right, so here comes the Hamiltonian equation. Uh, Hamiltonian. William Rowan Hamilton was born in 1806 and lived till 1805 and lived till 1865. He was a very smart dude. Did a lot of stuff when he was young, and it's good. But one of the things that he worked on was how to predict particle and energy. So H was a way to calculate what the value of the energy is. Google. But for many particles, whereas one particle was a simple equation, for many particles you're dealing with sigma notation. So it's you can see already that you're going to have to apply a transformation to a list, not just a certain number, because you're dealing with multiple particles. And so I'm not going to dive into any mathematical equations because I don't want to. So this is an example of a perturbation graph on multiple dimensions. Let me see if I can get this to work. This actually shows you perturbation of subatomic particles and their likeliness of existence in a certain location. So what are we dealing with here when we're talking about these things? We're looking for the probability density of a cloud of electrons. Where is the electron going to be? And that can be described as a wave. And it is good. This is a cross-section of that distribution. For a simple hydrogen atom, it's quite simple. You have a cloud, and it looks like a cloud. It is a cloud. And it has a distribution, normal distribution. So we do have a periodic table, obviously. We all know about that. It's good stuff, you know. But there's also nuclear physics, and that deals with a different aspect of our periodic table on a different scale. But this is a cat. People like cats. I thought I'd just throw it in there. It's important. Electrons can be excited to different states, and this is where eigenvalues help us, because these states are quantized, so they're this or that, and when it jumps up, it takes in a photon, it jumps down, it releases a photon. That's where we have light. Hydrogen atom has this many states. If you excite it, it'll jump to 2s, and excite it even more, it will go across this structure, getting bigger and bigger, and then collapsing to release light, a photon. Crystalline structures also exist in waves, in the sense that they vibrate at a certain frequency. Sorry, the information is a little chaotic right now. It's my first time doing this talk, and some of the things that are embedded in here are not coming through. Static susceptibility of interactive systems. Molecules in the structure. Awesome. So, Rayleigh-Schrödinger perturbation theorem deals with how subatomic particles get released and turned off, and the probability of them being released. That's not exactly accurate statement, but just keep going with it. You can give me corrections quite soon. So we have several subatomic particles and notations for them within the Feynman diagram. Not making sense right now. This is a state of Angela Merkel when she's really tired and has to listen to a lot of technical information that's not really presented well in this case. These are some of my sources. A lot of Wikipedia also, but these are some good places to look for more information. Thank you for taking a part in this show, and I will take your questions and comments now. Anyone? Bueller? Um, so I just got really interested in this topic, and I just started searching through the internets for it. Um, there's a fascinating way that they use Feynman diagrams um, to talk about how subatomic particles uh, eject from a collision. It's probably a better way of describing it. So a Feynman diagram has space on the y on the x-axis and the space and time, and as two subatomic particles approach each other, they come in on one side and leave on the other side. And during this time, they're passing through this wave where it's in a flux, sort of. Um, cool. And that's just the notation I wanted to show you again. So fermions and bosons are a good example of subatomic particles because they are. There's a major difference between bosons and fermions. Bosons are social, whereas fermions are antisocial. So if you take an equation to predict where their position is, where bosons would have two functions next to each other with a plus sign, where you can flip the x1 and x2 without a problem. In a fermion, you have to take those equations that predict its location, which is also a wave, and subtract the two. So that if you flip x1 and x2, you have to change everything else around it, and it becomes antisocial, meaning it can't be in the same location as the other. They will repel each other, like similarly poled magnets. Exactly, yeah. In the same location and quantum state. Quantum state, yes. Yes. So they cannot be in the same quantum state at the same time, and whereas bosons don't have that problem. And the way that that's expressed is by a negative, taking two functions as one being positive and one subtracted from it. So that if you replace it, you get the opposite. Yes?
Thank you.
Yeah.
Could you please explain to me the what you use Schrödinger perturbation for? Is it what problem does it solve, or what kind of technique?
So when you have a wave and you perturb it with some kind of energy, you excite it in a different way, making the wave oscillate at a different periodicity. The Rayleigh-Schrödinger perturbation theorem, RSPT, meant to create a way to estimate the result of the perturbation on the original system. So you have a wave equation, a simple sine curve, for example, and you perturb it with adding x to it. RSPT wanted to be able to approximate values closer and closer to what it is. They used Hamiltonian as a base, and they expanded from it.
So where do the eigenvalues come in, and the eigenvectors?
The eigenvalues are the base for the calculation for it, because you can't really take an analog value of a wave because there's so many different values in between the start and finish of what you're analyzing. Eigenvalues make it shorter list, kind of a Riemann sum of the wave. Yes, yes.
The Schrödinger equation in general is difficult
Difficult
for
to
the
solve.
energy you have.
Yep.
So you devise the state you can solve, and you say, okay, anything I don't understand, I do some kind of generalized Taylor expansion around the solution I understand, and that is what perturbation theory is.
Yes.
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 So yeah. So you go
So-
there
and
from,
it's not-
from the state that you know, for example, decomposed in harmonics,
Yes.
and then you want to describe something you don't know, and you make approximations to it because you cannot solve the whole differential equation.
It's too complicated.
That's the
And the more you
mathematical to
perturb-
complex.
The more complex it becomes, the more difficult it is. The
What do
more
you mean by complex it becomes?
more perturbation for it. If you're not calculating just the decomposition state, but decomposition state next to a star, and you have other values, variables affecting your system, then it becomes even more difficult to calculate. And so this helped. It's a tool to help you estimate the value.
Yeah, well, it's not only a tool, it's the only method, because we have not the capability to solve the complete equation. Even, for example, in a classical system with 3 planets, it's hard to do.
Yeah.
Yeah. So what
What
do
do you do?
Yeah.
Yeah.
So only very simple systems can be solved completely. And in terms of these, and that is what
But
But
when
the
you're talking about
eigenvalues and
simple system,
eigenvectors
it's
come in.
actually
you can decompose the problem into the base you understand. And these base are, for example.
so. Yes, that's true. And the simple systems you're talking about is just a simple hydrogen atom where it has one particle that you're trying to calculate, right?
Well, for the pure atoms, it's kind of doable, yeah.
Yeah.
So
yeah.
because you have only this charge in the center, and for one atom, for one electron, it's solvable. You get the sphere and all these others, and you get all these beautiful pictures of your density state. And what he talks about in a wave function is actually why is it so difficult to envision a wave function? It's a complex wave. Well, how do you envision a complex wave? The problem is that we don't have a good image of what this is. So if we treat it as a particle, it reacts as a particle. If we treat it as a wave, it reacts as a wave. But what it is, you cannot make a clear image about that in your mind. It's like a cylinder in 3 dimensions. If you look at 2 dimensions, if you look at from one side, it's a circle. If you look at from the other side, it's a rectangle. But it's a cylinder, but we cannot, see that. So that makes it difficult.
Awesome.
Right.
Anybody want to talk about anything else? Like what's for lunch? You know, what's good?
Well,
Anything quantum related?
if there's no more questions for now, anyone who wants to talk to the speaker, just go up to him personally, and we can go off to the next thing. All right. Give him a round.
Thank you guys. Too kind. Too kind.